In the last 2 or 3 classes, we discussed a stretch about coupling interaction, varieties of factors, varieties of information I gave you, right from the different features of coupling constant. And in the last class especially, we discussed about sign of the coupling, where I explained to you about how the spectrum changes, appearance of spectrum changes if there is a change in the sign of the coupling, because the sign of the coupling could be either positive, negative or 0, we do not know. Why the sign is important? I will come to that later, because sign of the coupling is extremely important, especially when in dealing with some of the structure of the molecule by using what is called RDCs, considering heteronuclei. If the sign of the coupling is not known, we make mistake in getting the geometry of the molecule. So, sign of the coupling is very important. And I also told you about the relative sign of the coupling. How do we get? By using Dirac model. I showed you the situation when both the spins are unpaired is a stable state, and we said 1JCH is positive, 2JCH is negative and 3JCH is positive. That is okay, that is the sign of the coupling. And how the relative sign of the coupling when they change, appearance of the spectrum changes. In the AS example, there are 4 peaks of equal intensity like this. When the intensity, let us say this is for positive J coupling, for the negative J coupling this will get reversed like this and this gets reversed. As far as we are concerned, spectrum remains unaltered. You will not know whether the transitions have got interchanged or not, but in reality it has happened. So, one dimensional NMR spectrum will not be able to give us the sign of the couplings. It is not possible to get it because the spectrum remains invariant. And I also showed you, I told you about magnetic equivalence. Magnetic equivalence is a situation where in a coupled spin system, all the chemical shift of the spins, coupled spins should be identical. They must be chemically equivalent because of symmetry operation or whatever it is. But at the same time, among when they are coupled to each other, coupling among each of the spins to other coupled partners should be identical. If I take the example 3 protons 1, 2 and 3, chemical shift of 1, 2 and 3 should be identical, they are chemically equivalent. Chemical shift of 1 and J coupling between 1, 2, 1, 3 and 2, 3 should also be identical. Then such a situation, these spins 1, 2, 3 are called magnetically equivalent spins. Magnetically equivalent spins gives us a single peak. Even though there is coupling among them, it will not get reflected. So, you will get only a single peak. And this magnetic equivalence need not be because of one coupling. If particular spin experiences 3 different couplings, take for example the benzene. Each proton of the benzene has an ortho coupling, meta coupling and the para coupling. Each proton experiences 3 different couplings with different strengths, but nevertheless benzene gives a single peak because all the protons are magnetically equivalent. Similarly, I took the example of ethylene also. And at the same time, I also mentioned to you all chemically equivalent spins are not magnetically equivalent, but all magnetically equivalent nuclei are invariably chemically equivalent. This is a term which you people should understand. With this, we will continue further today and discuss more about what is called complex multiplicity pattern. I already told you about multiplicity pattern, but how do we get complex multiplicity pattern? We will try to understand today among chemically equivalent spins and among different spins, etc. So, if there are chemically equivalent spins which we already discussed, if one proton is coupled to other group of proton like CH2, where 2 protons are chemically equivalent, it could be a single proton or it could be CH2 is maybe coupled to CH3. These are also equivalent protons, these are also group of equivalent protons. When it is coupled to group of equivalent protons, how does the multiplicity come? It obeys what is called 2ni+1 rule, where n is the number of protons in a group and I is the spin and plus 1. So, for example, n is equal to 2, let us say 2 protons are CH2. When it is one proton is coupled to CH2, 2 into 2 into half plus 1, it will become 3. When one proton is coupled to CH2, it will become a triplet, 3 line pattern. When one is coupled to 4, it will become 1 into 3 into half plus 1. Okay, I am sorry, 2 into 3 into half plus 1, that will become 4. So, we get 4 line pattern. one proton is coupled to CH3 will be a 4-line pattern, when one is coupled to CH2 will be a 3-line pattern. And the intensities of this multiplicity is given by what is called Pascal triangle. We will now go by this thing. But there are exceptions for this 2n+1 rule. One is a molecule like this, if we consider there is a symmetry along this axis and this proton will not couple to this at that. Now there is no coupling at all, no J coupling. Consider this one, if x and y are different, then this will couple to this. 2n+1 rule you can apply. This will couple to these two protons, 2 into half plus 1, this will become 3-line pattern. When this is coupled to this, again it will see 2 into 2 plus 1, 2 into half plus 1, they will get 3 peaks here. If x and y are different, if x and y are identical, you will not see the coupling. So there are exceptions for 2n+1 rule. So this is what you should, I wanted to tell you. Simple example is tetramethylsilane. We all know, I told you TMS is used as the reference for proton, silicon and carbon 13 NMR, and we have 12 protons. There is no splitting upon of these 3 protons, CH3 with this with this or anything. So it is a classic example of exception of 2n+1 rule. Okay. Now we will look at the multiplicity due to coupling among equivalent spins. Consider one proton, single, you will get single peak, that is what we have been discussing. Consider one proton coupled to another proton. How many peaks I expect? I expect 2 peaks, that is clear, fine. And it is this coupling gives you coupling between 1 and 2, this separation gives 1 and 2. Now we have equivalent couplings, equivalent spins. Consider equivalent spins such that not only these chemical shifts are same, coupling to this and this are same. For example, I look at one proton when it is coupled to two other protons, J12 is equal to J13, this coupling and this coupling is same, and I am looking at proton 1. Please understand this, I am looking at proton 1, proton 1 is coupled to 2, proton 1 is coupled to 3, J12 equal to J13, coupling is identical, then this will become a triplet because of 2n+1 rule. N is equal to 2, 2 into 2, spin of proton is half plus 1, it is going to be 3-line pattern, exactly what you are going to get. But this is called triplet in NMR. Intensity ratio is 1:2:1. We will come to that later. And this separation gives you J12. Now how does this triplet arise? I told you any proton coupled to other protons, one proton coupled to 2, we should get 2 to the power of n transition. 2 to the power of n is equal to 2, you must get 4 lines. But why we got 3 lines? That is because 2 of the lines are overlapped. How does that triplet arise? We will see now. Consider one proton, it is a single peak, it is coupled to one of the protons H2, it will become doublet of equal intensity. Now 100 intensity became 50-50 because when it divides intensity comes down. Further it is coupled to proton 3. What will happen? Exactly because coupling is identical, this will split into 2, this will also split into 2, but this line overlap because of exactly equal coupling. So 100 intensity become 50-50, then 25-25-25-25. These two 25 intensity lines are overlapped. So this is 1-2 coupling and this is 1-3 coupling. So 1-2 and 1-3 couplings are identical. As a consequence, what is going to happen is two lines of the peaks overlap and it appears as if 3 lines with an intensity of 1:2:1. This is how you get triplet. This is for a simple way of understanding, but quantum mechanically if you try to understand NMR, the reason why we say is it is because this is a beta beta state, this is beta alpha, alpha beta, and this is beta beta states, and these two are this identical states, indistinguishable. That is the reason why 2 peaks are overlapped and we get triplet. Clear now how we got triplet? We will go to the now, instead of 2 protons, let us say it is coupled to 3 equivalent protons. Instead of CH2 I made it CH3. Again I put the same condition, coupling 1-2 equal to 1-3 equal to 1-4. Chemical shifts are also same. Now I am looking at the proton 1. What is the pattern I expect? 4 lines. How did I get 4 lines? This is called a quartet. In NMR quartet is 1-3-3-1 intensity pattern. Okay. and this separation gives me couplings. How did this quartet come? We will generate it. Up to this thing we understood triplet, because up to this we knew early in the previous slide I explained to you how we got triplet, because two lines of this are overlapped. Now I have brought in the third proton. This third proton is also coupled to this with identical coupling strength. So what will happen? It was 1:2:1, intensity 100 became 50, and 50 and then it will overlap 25 25 25 25 25. These two 25s overlap, it became 25 50 25, 1:2:1 intensity. Now what I am going to do is I will bring in one more coupling, that is to H4. When H4 coupling is brought, again this will split into two peaks, this will split into two peaks. This 25 intensity became 12.5, here 12.5. This 50 became 25 here, 25 here, and then this will again become 12.5 and 12.5. Here 3 lanes are overlapped, 3 lanes of intensity 12.5, 2 from here, 1 from here, here 2 lines from here, 1 from here overlapped. Now what is the total intensity? This is 12.5, this is 37.5, 37.5 and 12.5. What is the ratio now? 1:3:3:1. You got a quartet. This is the intensity pattern you are going to see. Okay, this is the intensity pattern you are going to see. So in reality, the 4 lines of this 4 lines are called quartet, and this separation gives me 1 4 and 1 2, all are identical, does not matter. So now the 4 lines comes because this is the beta 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 state of 3 spins, alpha 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 states. This is what the way you have to understand. Here there are 3 possibilities: alpha beta beta, this is alpha, this is beta beta, beta beta alpha. 3 possibilities. Here alpha alpha beta, beta alpha alpha, alpha beta alpha. These 3 such possibilities are there, and they are indistinguishable. That is why 3 intensity. That is why here also 3 intensity. This is the way you have to understand NMR. But if you are worried about mathematics and quantum mechanics, you do not have to worry. There is a way to understand this. This is called a Pascal triangle. How do you understand by a Pascal triangle? Let us say I have n coupled spins, spin of nuclei. First, when there is only one spin, you have only one line. When you have 2 spins, each will become equal intensity half half, 1:1 intensity ratio. When there are 3 spins, we get 1:2:1. That is what we worked out. When there are 3 spins, we have 1:3:1 intensity, okay, and we have 4 spins, 1:4:6:4:1. Like that we can start getting intensity pattern. They obey what is called Pascal triangle. Okay. How do you arrive at this intensity? You can, there is an easy way of generating the intensity in a Pascal triangle. Like first you put one single spin, not coupled to anything. It is coupled to another spin, one spin, each become 2 2. In third spin, when you bring in two other spins, 2 spins are there, one spin plus another spin, 2 spins. How do you generate the intensity? Add 1 intensity at the top of that, 1 plus 1 you add it to 2, this one you retain here, this one you retain here. Only these 2 you add up and it will become 2. If you have 3 spins, what you will do? Write this one here, add up these 2, 1 plus 2 3, add up this 1 plus 2 3 and this put 1 here. For example, if you have 4 spin, put 1 here, add here 1 plus 3 4, 3 plus 3 6, 3 plus 1 4 and put 1 here. This is the way you generate the intensity pattern by looking at the Pascal triangle. Okay, this is how you are arrive at it. Actually, it is a layman way of understanding. But what is the way to understand the intensity of the Pascal triangle? It is nothing but coefficients of the binomial expansion. When there is no spin coupled to other, when identical, only one single spin, let us say A. When you have 2 spins, A plus B. When you have 3 spins coupled, make it A plus B whole square, which is nothing but A square plus 2AB plus B squared. What is the intensity? 1, 2 and 1. That is the intensity ratio, 1 to 1. What about A plus B whole cube? 1, 3, 3, 1. That is intensity ratio 1, 3, 3, 1. But if you want to understand that, there is a way to understand by combination also. These are 0, 1, 0 C 0, 1 C 0, 1 C 1, like that you can understand. This is nothing but the coefficients the binomial expansion. So, Pascal triangle, that is how we generate. Now, the question is total transitions, I said when n spins are coupled is 2 to the power of n. Where are those n's? Please remember here 2 peaks of equal intensity, one is coupled to other one, that is fine. When it is coupled to 2 equivalent spins we get 4 lines, but remember 2 of which are overlapped. So, 2 to the power of 2 is 4, there are 4 peaks, only 2 are overlapped. Similarly, when you have 2 cube, okay, then we can see there should be 8 peaks here, 2 cube 8 when it is coupled to 3. See 3 peaks here and here are overlapped, that is why intensity 3 3. So, total is 8 intensity, 8 intensity is 8, that means there are 8 peaks, 3 of them are overlapped here, 3 of them are overlapped here. Like that you can get here 16 peaks, 4 are overlapped here, 6 overlapped, 4 are overlapped here. Like that there is no violation of the number of peaks that you are seeing. The number of peaks what you are going to see is still to the power of n only when one proton is coupled to n other protons. But because of equivalence of magnetic equivalence or chemical equivalence, J couplings are identical, some of the peaks are overlapped. So, intensity is different, but the total number of peaks, if I take 1 to 1 intensity, total number of peaks are 4 only, but 2 peaks are overlapped. Same way for others you have to understand. So, with this we will go into the common splitting patterns among coupled spins or groups of coupled spins. Let us see how we get this one. I consider one spin coupled other spin, we get each will be doublet, fine, of intensity 1:1. This is chemical shift and we get J coupling here. Now, let us say one spin is coupled to 2 equivalent spins. Here A and X was there, here there was no proton, here I brought proton now. These two are equivalent, AX and AX2, we already worked out. When A is coupled to 2 protons, it will become a triplet, that is what we worked out because of the Pascal triangle. Whereas, if I look at H will be coupled to only single proton, so it will be a doublet. You got the point. When I have CH coupled to CH2, CH is going to be a triplet, whereas CH2 is going to be a doublet. So, that is why X is doublet, whereas CH is going to be, see this CH is going to be a doublet, I am sorry, this CH is going to be triplet, this CH2 is going to be a doublet. This is what it is. This is called triplet and this is called a doublet. So, center of this gives you chemical share of A and X and separation gives you J coupling. Now, on the other hand, I consider a situation where one CH proton is coupled to CH3 group. Just now we worked out when this is coupled to C3 chemically equivalent, 2Ni plus 1 rule you apply, or with the you can get the intensity by Pascal triangle. N is equal to 3 here, 2 into 3, spin is half, then you get 4 lines, that is what you get. When one proton is coupled to 3 equivalent methyl groups, 3 equivalent protons, you got 4 lines. But the intensity of the 4 line is Pascal triangle. But what about these 3? If I look at the CH3 group, but this is seeing only the CH. CH has only 2 states, alpha and beta. So, it will be a doublet. You understand? When CH proton is coupled to CH3, CH is going to be a quartet, CH3 is going to be a doublet. And this is entrance again is a chemical shift of CH, this is a chemical shift of CH3 and separation gives you J coupling. Easily you can identify that. We will go further. Consider a situation where we have a molecule like this, CH2 and CH3, there are 2 groups and hypothetical molecule. You get a pattern like this. How? Very easy to understand. This CH2 will see 3 equivalent protons. Using 2Ni plus 1 rule, it will become 4 lines. This CH3 sees 2 CH2 coupled to 2 CH2. Use 2Ni plus 1, 2 into half plus 1, it will become 3 lines. Because they are equivalent groups, we have quartet and a triplet. This is called a quartet and this is called a triplet. Triplet is always intensity ratio 1:2:1, quartet is 1:3:3:1 intensity ratio. You understand? How we can get the multiplicity pattern? When CH2 is coupled to CH3 or CH3 is coupled to CH2, we get patterns like this. And again, center of this gives you chemical shift of CH2, this center gives you chemical shift of CH3. Okay. This is called a quartet, this is a triplet, and separations gives you coupling between CH2 and CH3. Very easy. So, how do you measure the J coupling? Already I told you, this is very easy. If I have a pattern like this, adjacent peaks you have to consider. You cannot measure the separation between this and this. Adjacent peaks of the coupled multiplet pattern gives you J coupling. In this molecule, CH3 CH2 is there, and this is coupled to this, and it will be triplet or quartet, does not matter. This separation between the adjacent peaks, if you measure, you get coupling constant. You cannot measure peaks which are far away, only adjacent peaks you have to consider. Same way here, there are two CH2s, this will become a triplet because of this will become a triplet because of this, and this will give you two triplets, and my separation gives you coupling. Okay? Very easy. Now we will see what happens. This is a simple molecule, but in reality you are not going to see only this type of simple molecules. You come across various complex multiplicity patterns. How do we get that? How do you get the splitting patterns when a single proton is coupled to groups of protons or several groups of protons, both chemically equivalent protons or not, and then how the multiplicity comes? Several examples we will take now. I take a hypothetical molecule like this. When I have considered a proton here which is highlighted in green, it is coupled to two things now, one CH proton and also CH3 protons. Understand the point. Proton A is coupled to proton Y, it is a single proton. It is also coupled to CH3 which is 3 protons, which is X. So, this is AY, I call it JAY, this is JAX. Okay. Proton A coupled to Y is JAY, proton A coupled to X is JAX. Now, I will put a condition AX equal to AY, that means the couplings are identical. This will experience coupling, identical coupling with this and this. Then what is the pattern you are going to get for proton A? If I observe proton A, what do you get? I get a pentet. Very surprising. How did you get this pentet? Of course, center of this is a chemical shift of this proton, and this will give you couplings. Separation of the adjacent peaks will give you coupling. But how did you generate the pentet? How do you know it is a pentet? Remember, it is because of the equivalent coupling. What I will do is, I have put the condition AX equal to AY. A is split into quartet because of X. That is correct. That we have already discussed. Because of magnetical equivalence, according to 2Ni plus 1 rule, this will become a quartet because of 3 protons. Quartet of the intensity 1, 3, 3, 1, that we have been discussing today. But simultaneously, this A is also coupled to Y, but it is a single proton. As a consequence, A will become a doublet, but is already coupled to this one, become a 4-line pattern, quartet. But now because of the coupling with single proton, each line of this quartet will become a doublet. This is the intensity ratio 1:3:1, each will become a doublet of the intensity half. This intensity again half 1.5 1.5 exactly at the center. You see, it will be from the center on either side you will see doublets. Again from this center you will get half line, again half of lines. I have put different colors for you to understand. You see, this is one color, this is another color, another color and another color. Each line is split into two lines, half of intensity, and this intensity is half of, this is 1.5 by 1.5, but 2 lines are overlapped here because of identical J coupling. So, calculate the total intensity now. This become 0.5, 3 or 2, 3, 2.5. What is the intensity ratio? Now, it is a pentet, intensity 14641. It is called a pentet because you have 5-line pattern. See, you have 5-line pattern here, and that is why this is called a pentet of intensity 14641. Please remember, when one proton is coupled to CH3 and another CH2 single proton, if the coupling constants are identical, you will get a pentet. What happens if this proton is coupled to two CH2s? One proton is coupled to two CH2s. That is also interesting. Earlier I took the example of CH and CH3, but now taking the example of both CH2s coupled to this proton A. What will happen? When this is coupled to one of them, again I assume the condition AX equal to AY, couplings are identical, that is my condition. Okay, I put the condition JAX equal to JAY. Because of one of the methyl groups, when it is coupled, it will become a triplet, that we already discussed. When this proton coupled to CH2 group, 2Ni plus 1 rule will become a triplet. But now what is happening? It is also coupled to another CH2. What that CH2 will do? It will ensure that each lane of this triplet is further split into a triplet. Each lane will become another triplet because of another CH2. So like this is a 1-to-1 intensity. Now because of another CH2, it will split into another triplet, intensity becomes 0.25, 0.5 and 0.25. This will also be like that, and this will also like that. And interestingly, because of the coupling is same, this here overlap, this line will overlap, this line also will overlap. Now calculate the intensity now. What is the intensity? 14641 ratio. That is also a pentet. This is where the confusion comes. When you want to analyze the NMR spectrum, you will see that a single proton coupled to another proton in CH3 with identical strengths also gave pentet. One proton coupled to two CH2 protons with identical strengths also gives a pentet. This is where the beauty comes, and you have to have the knowledge of unraveling this multiplicity to get the information about the structure of the molecules. This is another way of getting a pentet. Now we will go to a complex example. A CH proton is coupled to CH2 and CH3. Extend the logic. What is the type of pattern you get for this proton? It is coupled to, let us say, CH3, again coupling is same. It gives rise to a sextet now, not pentet, sextet. How? We will work it out. Take this one, when this CH2, this CH is coupled to CH2, will be given rise to a triplet. What is the intensity? 1-to-1. And each line of the triplet is split into quartet because of CH3. 2Ni plus 1 rule you apply, and now each will become a quartet. And again this is a quartet, this is again a quartet. You see, I am showing in different colors. Because the coupling is same, some of the lines overlap here. Now calculate the intensity. If you put the intensity, this turns out to be like this, and this intensity is 1:5:10:10:5:1. This is sextet, 6-line pattern. Remember, when one proton is coupled to another CH2 and a CH3 group, you get a sextet pattern. I use this while analyzing the spectrum at a later stage. That is why I am giving all this example. Now you may ask me a question. Here I took CH2 first and then worked out this multiplicity pattern and get a sextet of intensity, this one. Why did I take CH2 first? Why not CH3 coupling first? This is coupling to both of them. I took sequentially this first and then this one. Why not I take the reverse order? What happens if I consider CH3 first? Then it is a quartet because of 2Ni plus 1 rule. That is correct. But now each line of the quartet is split into a triplet because of this. We will see what will happen. One triplet, another triplet, another triplet, another triplet. Now calculate the intensity. Same, there is no difference. This also sextet, same intensity ratio. So what did we understand from this? If you are generating a multiplicity pattern, then order in which you take the coupling is immaterial. For this CH proton, you consider this coupling first or this coupling first, does not matter. Totally both of them are coupled simultaneously. For working out the multiplicity pattern, the splitting pattern is invariant with the order of the coupling chosen for obtaining the multiplicity. How do you get the multiplicity? Whether you take CH2 first or CH3 first or converse of them does not matter. the total spectrum appearance finally the multiplicity pattern remains identical. So, this is how when you are working out multiplicity pattern by using this type of Pascal triangle approach, it does not matter which one you take first, which one you take second. So, we will take the example of another one. A CH proton is coupled to two equivalent CH3 groups. Now, you should understand, already you know what is the type of pattern we expect. This CH3 coupled to this CH coupled to this CH3 will be a quartet, and each layer of the quartet is further split into a quartet because of this, and because of the overlap of the transitions, what is going to happen? We are going to get what is called a septet, 7-lane pattern, if the couplings are equal, AX and AY are identical. This is the intensity ratio 1, 6, 15, 20, 15, 16 to 1, 6 to 1. And now we will see what is the, how do you generate the septet pattern. We know one proton coupled to CH3 group is going to be a quartet, intensity ratio 1331. Now it is coupled to another CH3, each lane of the quartet becomes another quartet like this, different colors you see, but interestingly these lines here overlap, here overlap, here overlap. Calculate all the intensities what I have written at the top here, and if you put the intensity, calculate the ratio, it is like this, it is a septet, 7-lane pattern, and this is how you get the septet. So, this is how we arrived at the splitting pattern when one proton is coupled to remaining other protons. Now, some complex multiplicity pattern will be there, which I am going to discuss in the next class. Right now, I have given you umpteen number of examples today to obtain the multiplicity pattern. What happens when one proton is coupled to two protons, when one is coupled to three protons, or two CH2s are coupled to single proton, CH2 proton is coupled to CH and CH also coupled to CH3 simultaneously. How do you get the multiplicity pattern? I said when one proton is coupled to CH2, it will be just a triplet. When it is coupled to CH3, it is a quartet. When it is one is a CH2, other is a CH3, we get triplet and quartet in the spectrum. We took the example of one proton coupled to two different groups. When one proton is coupled to CH2, it is a triplet. It is also coupled to another CH2, it is a triplet. Each lane of the triplet will become another triplet, which I saw as a pentet. And then similarly we saw when one is coupled to CH2, one CH3 and another CH2, we got sextet. When both are, one proton is coupled to two CH3, I showed it is a sextet. And I also showed the multiplicity pattern and the intensity can be easily worked out in a simple way. But then order in which you take in arriving at this multiplicity pattern is immaterial. Whatever the order you take, multiplicity pattern finally remains invariant. And we took several examples of getting sextet, pentet, and septet, everything. We will continue further and few more examples we will take, and then we will see we will become confident enough to analyze 1D spectrum of varieties of molecules in the subsequent classes. Of course, still lot more I have to discuss about the few more multiplicity patterns. What do you call when you have many things are coming at a time? How do you explain this one? We will come to that in the next class. Thank you very much.